Let's see. Oh, Jack, how are you? Now let's go. Alrighty. Uh, alrighty. So this is gonna be our chapter 7, which is gonna be talking about work and energy. So we started this course talking about your displacement, which we defined it as a change of, let's say, of our x, which is going to be your x final minus x initial. So x final, that's going to be our final position, and that's going to be our initial position, which we gave it your letter D. You take this displacement and divide it by your time, and what you're going to get, you're going to get your velocity. Actually, write that letter down. Velocity. Now, the unit for your displacement is going to be again in meters. So this is going to be in meters. For your time is going to be your seconds. So this is going to be your meters per second. Actually, let me go ahead. Velocity, which is going to be your V, which is going to be in your meters per second. Now, you take this velocity, which we call the letter V, you divide it by your time. What you're gonna get, you're gonna get your acceleration, which we give it an A, which is gonna be in meters per second square. We multiply this acceleration by your mass. So this is gonna be, you get this acceleration, you get multiply it by your mass, and your mass is gonna be in kilograms. And this is gonna be your acceleration over here. This is gonna equal to what? Actually, let me go better. And that's when we talk about your force. And it's going to be your F, which is going to be in your mass is going to be in kilograms. Acceleration is going to be your meters per second square, kilograms meter per second square. And that's what we call the Newton. And we give it a big letter N. And that's going to be your unit for your force. And then we saw in the last chapter, we get a different color, where we took the mass, this little fella, and we multiplied it by the velocity, v. And this one we talk about momentum. Again, we give it the Greek letter rho, which is going to be the units for it. We saw this from last chapter. It's going to be kilogram meters per second. Now, I would like to introduce a new concept, a couple of concepts. The first one is your work. So we have the mass, we have the force that we talked about. You're going to use this force in some kind of distance. And that's where we talk about the work. So we give it W. Now, we said we defined the force as your mass times acceleration. And we define your distance or displacement in meters. So your force is going to equal your M times A times your distance. So your work makes you mad. That's why it's important to take a vacation if you have to work, because too much work makes you mad. Your mass times acceleration times your distance. You take this work and you divide it by your time, and that's what we talk about your power. And you give it a big letter P. And now the units for power, your work is going to be in joules. Actually, let me go ahead. I forgot to do this. So let's do the units for this one. This one is going to be your kilograms, meter square per second squared. And that's what we thought, well, that's what we call the joule in honor of James Prescott Joule, which is going to be your unit for your work. So basically, your power is work over time, so it's going to be joules per second. And that's what we call a watt. So let's look at this more detail. So the work done by a force the work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance through which the object acts on. We're going back over here. So your work is your force multiplied by your distance. Let's take a look at this little video. We have a little video to look at. All right, here's our first video. So in our first video, we're using some kind of weight. So that weight has a mass that's acting up upon by the acceleration of gravity. And it is striking the nail. Now, notice that the higher the weight, the further the distance, the further the nail goes through. So your force times your distance increases the higher your distance. If it's the same force, you're increasing distance, so it's increasing, which means your work is increasing. So here's one that's actually higher than all of them. And you notice that how fast, how the third nail is going to go down. The greater the kinetic energy of the fallen force, the greater its work is going to do. And that's what we're talking about. We're talking about your work and your energy. Come back over here. So your work is your force times your distance. And we define the force as your mass times acceleration, which is going to be in newtons. And your distance, your displacement or your distance is going to be in meters. So your work makes you mad. Too much work makes you mad. Mass times acceleration times your distance. This is your mass. And that's your acceleration, which is going to be your meters per second squared, as we defined a second ago. This is going to give you a kilogram. So again, this is going to be, let me get a different color, be kilogram meters per second squared. And that's what we call the Newton. Sorry, that's what we call Joule, in honor of James Prescott Joule. So basically, your joules is how much force per distance. So it's Newton meters. And again, we give the joule, letter J, which is going to be your unit for your work. Now, when we talk about energy, we need to introduce two concepts. The first one is going to be your potential energy. And your second one is going to be your kinetic energy. So I'm going to give you KE. Now, your kinetic energy is the energy of a moving object. Potential energy is basically stored energy. Now, your kinetic energy is going to equal to 1/2 mv squared. M is your mass, mv, that's your velocity. So let me actually write it down. So your Ke is going to equal to 1/2 mv squared, or let's say the mv squared over 2, which your mass is going to be in kilograms. Your velocity is going to be meter squared per second squared. Actually, I think I forgot to actually, yeah, kilogram meter square per second. So I forgot the distance for over here. All right. So this will be kilograms per kilogram meter square per second square, and that's what we called the joule. So the joule is the unit of energy. It doesn't matter what kind of energy. It's your work, it's kinetic energy, or it might be your potential energy. In this case, our potential energy that we're going to be talking about, which I'm going to explain in just a second, is your gravitational potential energy, which is going to equal to mass times gravity times your height, which in units, let me get a different color. In units, we're also talking about kilograms for mass, your gravity, which is 9.8 meters per second square. So this is going to be your meters per second square times the height, which is going to be meters, which is also your joule. So it doesn't matter what kind of energy you're talking about, whether kinetic, potential, whether it's work, we always going to have joule for the unit. So going back over here. So the work done by the force acting on the object is equal to the magnitude of the force multiplied by the distance with the object which the force acts on, which equals to force times your distance, which makes the work makes you mad. Too much work makes you mad. Your mass times acceleration times your distance. Now the unit for the work is going to be your joule, which is defined as Newton meters, which is kilogram meter squared per second squared. Again, it's named after James Prescott Joule, which he died in 1889. Now, the cool thing about James Prescott Joule, he actually, his dad owned a brewing company, so he grew up well off. He in college, he actually went to school and he was educated under Professor Dalton in chemistry, and he actually worked with Dr. Calvin, the creator of the Calvin scale. He then took over his dad's business and decided to go from steam to electric way to brewer his brewery. So he was actually the grandfather of thermodynamics. That's where he invented the thermodynamics. He also used to play pranks with him and his brother with electricity because he was so fascinated by it. Now, he did a little experiment. Now, in an experiment, he got a small pedal wheel inside a container of water and he put a weight in the end. Now, he noticed when the weight goes down and the pedal moves around, that the temperature rises in there. And he concluded that the same amount of work always produced the same amount of heating. So there was some kind of work done. Now, one thing that we actually also define is the power. Now, the power is the rate of doing work, which is basically how much work per time. Now, you work, let me go ahead. Let me go ahead over here on my little notes. So your power, let me go ahead and define the power, which is how much work you are doing per time, which is how much joules per seconds. That's why the power company is called the power company. We charge you how much joules you are using per time, how much joules per second, how much energy per time that you are using. Now, the best way to explain the energy is with a pendulum. So if you ever play with a pendulum, this is our pendulum. It keeps on going back and forth. When the pendulum goes back and forth oscillating, your potential energy over here will be the highest. Your kinetic energy will be lowest. Going in the middle, that means your kinetic energy can be highest. Your potential energy will be the lowest. Or your potential energy goes back up high. Kinetic energy goes back up low. All right. So the watt is how much joules per second. We talked about that. So energy, let's talk about energy. Energy is the property something has it that enables it to do work. Now, the first form of energy we talked about is the kinetic energy. Your kinetic energy is the energy of a moving object. Now, this kinetic energy depends on two things, your mass and your speed. And it's going to equal to 1/2 mv squared. So, for example, what is the kinetic energy of a 1,000 kilogram car at 10 that's going at 10 meters per second? Now, let me go ahead and write down my 4 rules. So this is Dr. Malek's 4 rules. And if you ever watch Marvel, this is your Fantastic Four. So this is Dr. Malek's Fantastic 4 rules. Number 1, write down the info. Number 2, something is going to equal to your double question mark. Number 3, write down the equation. And number 4, like plug and play, we call it list plug and solve. So let's do this example, shall we? So you got a 1,000 kilogram car at 10 meters per second. So you got your mass is 1,000 kilograms. Let me write down the info first. And your velocity is 10 meters per second. What are you looking for? You're looking for kinetic energy. And you know that kinetic energy is going to equal to mv squared over 2. And in this case, it'd be 1,000 times 10 squared, which is 100, divided by 2. In this case, what you get, 50,000 joules, which is 50 kilojoules. Awesome, awesome. And we get the right answer. Now, your potential energy is stored energy. Example stored energy, your gravitational, your spring, which we're going to be talking about later, and your electromagnetic, which we should be talking about in physics too. Now, energy can be transferred from one form to another. It can go from kinetic to potential, potential to work, etc. You cannot create energy or destroy it. Energy cannot be created or destroyed. It only can be transformed from one form to another. So let's go ahead and watch a little video about that. All right. So in this video, we have an energy wall. And it has a V-shaped bottom. Now, if you let the ball go, it will just oscillate back and forth. And notice that you do not have enough sufficient energy to let the ball escape through the top. So the question is, how much higher must the ball be released in order for the ball to escape the energy well? Let me go ahead and get back. So how high must the ball be to release to be escaped? Is it going to be below the low side, equal to low side, slightly above, or much above? Go ahead and guess your answer while I do the next video. The ball has to be just slightly higher above the other side in order to have enough energy to go over the track. Okay, well, let's watch another video. Now, in this side, we have three hills, a steep, steeper, and the steepest. Now, how high we have to put the ball on each side in order for it to go to the other side? Which side would be highest when we release the ball? Is it the first side, the steeper, or the steepest, or the steepest? Number one, number two, or number three? Which one do y'all think? Go ahead, think. Let's go ahead and look at the other video. Here's your ball going in first track. Here's the ball released on the second track. And here's the ball released on the third track. So they all, because we start from the same place, they all rise to the same height, no matter how steep it is, because it has the same amount of energy in all three cases. Now, we talked about a pendulum. Let me go ahead and where's my when we talked about a pendulum, we said the pendulum is the best example about going between potential and kinetic energy. Let me go ahead and show you a video on that real fast. Here it is. So here's the pendulum going back and forth. Notice right over here that our kinetic energy is highest, your potential energy is lowest. Both kinetic and potential energy equal to the total amount of energy that they have in the system. So it goes up to the highest point. Notice that the kinetic energy is the lowest, potential is highest. Again, going down, kinetic energy goes higher, potential lowest, and then up to a point where the potential energy starts raising up to the maximum where kinetic energy raises down to a minimum. Now we have usually a bet over here. So this guy is going to bet his life on science. So what would you think if he left the ball? What would happen? So he's going to release the ball from directly from in front of the stage. Do you think his head is going to get smashed or not? Let's see. When the ball is released, it comes back to the same spot because it has the same energy. So it does not even touch it because he released it from in front of his nose. So it goes back to the same spot. So in order to transfer energy to an object, you need to exert a force on that object. So let's say you have an object with mass m, and let's say you give it a force F to move it some kind of distance d, put it in another position. And again, that's your work, which is your force times your distance, which actually is you going in a vector going on a distance. So it's going to be your F cosine theta times your distance d. Or actually, let me just say your FD cosine theta. In this case, you're going in here. What's your theta? Your theta is 90. So this is going to equal to FD, sorry, 0, cosine 0, which is going to equal to 1, which is going to equal to force times your distance. That's if you're going parallel to the ground. Now, what if you're not going to parallel to the ground? Let's say, you travel a lot, like me, and let's say you have a suitcase. The suitcase has a wheel on it, and you are pulling the suitcase this way. Now, how are you pulling the suitcase? Well, if you are pulling the suitcase, that means you're going to have a force F going on this way. This force F is created because your F in the X direction and F in the Y direction, as discussed in chapter 2, which is going to equal to F cosine theta. This is going to be F sine theta. And this is your angle theta that you're actually going in. So the work done, which is going to be your force times your distance times the cosine, the angle between them. Let me go ahead. D is your displacement, while the force is on it. And F, again, is your force. So work is the amount of joules of energy given to an object in the system. Now, your work is positive when the force is giving energy, and it's negative when the force is taking away energy. Your net work is going to be your summation of all the works for your work for your first system, your second, your third system, which is going to be all the summation from n equals 1 to infinity to W of n, which is going to be all your net forces. That looks like an E. Times your distance. This is going to be your net work. So your work makes you Too much work makes you mad. We define the mad as mass times acceleration times your distance. Now, if you remember from chapter 2, we had the kinematic equation, Vf squared equals V initial squared plus 2AD, which means that if you actually solve for AD, what you're going to have? You're going to have final square minus initial square divided by 2. Oh, what a coincidence. Here's your AD over here, and here's your AD over here. So we can go ahead and substitute this in there. So this means that the work is going to equal to your mass times your final velocity squared minus your initial velocity squared divided by 2, which you can take the 2 out, so it'll be m over 2 times Vf squared minus Vi squared, which is going to equal to m V final square over 2 minus m V initial square over 2. And we define the kinetic energy. Remember what we defined the kinetic energy as? Let me get a blue. We define the kinetic energy as mv squared over 2. So this makes this one your kinetic energy final. And this little fella, that'll be your kinetic energy initial. So basically, your work is going to equal your kinetic energy final minus your kinetic energy initial, which is going to be your change in your kinetic energy. So let's go back to our slides. So the total energy for poles stays the same, but continuously exchanges between kinetic energy and potential energy, which we talked about the pendulum. We just saw the video. We also talked about the work, which is going to be actually your force times your distance times the cosine the angle between them. So for instance, find the work done if the force is 45 newtons and the angle 50 degrees at a displacement of 75 meters. So let's go ahead and do this example. So in this example, the work was 45 newtons. Your distance is 75 meters. And let me go ahead. And your angle is 50 degrees. And I'm sorry, this is your force, not your work. And you're looking for your work. In this case, your work is FD cosine theta. In this case, it'd be 45 times 75 times cosine 50. And in this case, it should equal to 2,170 joules. That's correct. Okay, let's do another example, shall we? So the truck is accelerating at a rate of 1.5 meters per second square. The mass of the crate is 120 kilograms, and it does not slip. The magnitude of the displacement is 65 meters. What is the total work done on the crate by all forces acting on it? So let me go ahead and write down my information on this. This is example 3. Your acceleration is 1.5 meters per second square. Your mass is 100 kilograms, 120. and your distance is 65 meters. In this case, you are looking for the work done. And you know the work makes you mad, which in this case would be 120 times 1.5 times 65, which is going to equal to 1,100, 600, 11,600 joules. Now, notice we didn't put the cosine theta. We can actually go cosine theta. In this case, our cosine theta would be cosine 0, which is going to equal to 1. So it's going to be f cosine theta. You go in. Now, so your work is energy transferred by the force. The energy is the ability to do work. And your work is your force times your distance, which makes you mad. Now consider the net forces. The net external force is acting on an object. The object is displaced in a distance s in the same direction as the net force. So basically, your work is summation of all your forces times your distance. So your work makes you mad, and we said that is going to equal to, we just derived a little while ago, is going to equal your kinetic energy final minus your kinetic energy initial, which is going to be your change in kinetic energy. Now this, your W equals your change in kinetic energy. That's what we call your work energy theorem. So let's go to another example, shall we? We already done this, and we actually worked on the energy. Yeah, so when the net external force does work on an object, the kinetic energy of an object changes by the amount of work done on it, which is your 1/2 mv final squared minus 1/2 mv initial squared. So in this example, we have a massive space probe is 474 kilograms, initial velocity is 275. If the 56-meter Newton force acts on the probe through the displacement of 2.42 times 10 to the 9th meter, what's its final speed? So in this case, this is example 4. Your mass is 474 kilograms. Your initial velocity is 275 meters per second. Now your force is going to equal to 56 millinewton, which is going to be 56, 5.6 milli is 10 negative 3. So it'll be times 10 negative 2 newtons. And your distance is 2.42 times 10 to the ninth meter. And you're looking for your final speed. And we define, okay, well, let's go ahead. Let me actually get a different page on this. Let me actually, I'll put it over here. So we define the work as your 1/2 mv final square minus 1/2 initial. Let me just go ahead and put it on. So we get the mass, we get the final. We're looking for we get the initial. We're looking for the final. We don't have W. Now W is going to equal to what? FD cosine theta. We can assume that theta is going to 0, so that's going to equal to 1. So in this case, your F of D is going to equal to M VF squared over 2 minus M VI squared over 2. So this is going to be 5.6 times 10 negative 2 for your force times your 2.42 times 10 to the 9 is going to equal to 474 VF squared over 2. Yeah, I should move this a little bit. Minus 474 times your 275 over 2. Which means if you actually plug this in, your VF should equal 805 meters per second. Now, supposedly you got, let's talk about potential energy for a second. Supposedly you get a basketball. So let's say you get a ball, your ball over here, and you drop the ball on the floor. And right behind the floor, so this is going to be your initial height. This is going to be your final height that the ball is going in. And what's pulling the ball down? Gravity. Now, what's your work is going to equal to? Your force times your distance. In this case, your force is going to be your mass times your gravity multiplied by the distance, which we call height. Actually, let me go ahead. So your distance in this one is going to be your delta H, which is going to be your H initial minus H final. So this is going to be your H initial minus H final. That way it will be positive one. So this is going to be your H initial minus H final. So your work is going to equal to your mass times gravity times H initial minus mass times gravity H final. And that's what we call your potential energy. Remember, we call the potential energy as your mass times gravity times your height. This is your potential energy initial. This is your potential energy final, which is, if you see, it's going to initial minus final, so it's minus delta PE. You see, let's say we have a table. Let's say you got this table over here. On the table, you have a book. You get a different color for the book. This book is on there. Now, this book is going to be pulled down by gravity to a distance, or let's say this is the floor, the distance h, and the book has a mass. Your potential energy that has it on it is going to be your mass times your gravity times your height. So in this case, you get your work is going to be your mass times gravity times your height initial minus your mass times gravity times height final, which is going to be minus delta PE. Which again, when your PE equals mgh, you're talking about kilogram, your G mass, your G is gravity, which is 9.8 meters per second squared. Why is it meters per second squared? Because it's acceleration. And H is the height. So it'll be kilogram meters per second squared times this meter for this one. It's going to be meters, kilograms. So it'll be meter squared. And that's what, again, you go back to joules, which is the unit for your potential energy. So the gravitational potential energy is the energy that an object of a mass has by virtue of position relative to the surface of the Earth. And it's measured by the height of the object relative to an arbitrary zero level. It's going to be mgh. So let's say we have another example. Let's say we have a girl on a swing 2 meters above the ground at the end of her motion and 1 meters above the ground at the lowest point. What is the girl's lowest speed? So let's do this example. So same thing. It's a girl. Let's say this is our ceiling. Here's our swing where the girl is at. You're gonna go in this side, and it's gonna go inside, kind of like a pendulum. So it's exchanges between kinetic energy and potential energy. You can, and let me just put down the information. So above, H final is gonna be 2.2 meters. H initial is gonna be your 1 meter. So out of both of them, your delta H is gonna be 1.2 meters. So your kinetic energy equals your potential energy, which kinetic energy be mv squared over 2 is going to equal to mgh. Notice that the masses cancel out, which means that the v squared is going to equal to 2gh, which means that v is going to equal the square root of 2 times g times h. And in this case, is going to be 2 times 9.8 times your 1.2, and is going to equal to equal to 4.8 meters per second. Let's check our work. Correct, 4.8 meters per second. Now, let me go ahead and talk about conservative and non-conservative forces. So conservative force is work done by a force depends on the initial and final position. So let's say we have an elevator. Let's say this elevator has a mass of 5 kilograms and is pulled down by the weight. Now this elevator goes down, let's say 6 meters. So first of all, what is the weight of the elevator? Well, we just made it like a little small elevator, but the weight WEIGHT is going to equal to your mass times gravity which is in this case, it'd be 5 times 9.8. So it'd be 49 newtons. So now let's go up and down. Let's say you got 1, it goes down. Number 2, the elevator goes back up. Number 3, it goes back down again. And again, this is going into 6 meters, 6 meters, 6 meters. We said that the weight was 49 newtons. For number 1, the work done is going to equal to what? Your force multiplied by your distance, with your mg, which is going to be 49 times your 6, which is going to be 294. For the first one, it's going to be 200 minus, is going to be 294 joules. For the second one, the work done is going up against this, would be minus 294 joules. For the third one, the work done is 294 joules. Add them all up, and what you get? 294 joules. And that's what we're talking about, conservative forces, which basically you conserve mechanical energy. Now let's talk about non-conservative forces. Which basically they do not conserve, what do you think? You're right, mechanical energy. So let's say you got an object that's going on, say on the floor, and you move it at a velocity f. What's going opposite of it is your friction. Now, let's say you take this object and let's say you take it back and forth. So you keep going back and forth. Basically, the thermal energy, what will happen? The thermal energy will go more and more. You're going to have more and more heat. You take that and you go back and forth. You're going to have, it's going to get hot. So the thermal energy will go larger or bigger. That means that the work done depends on the path. So basically, your conservatives are conservative. When you have a force, you deal with gravitational potential energy. When you have the friction, you don't have gravitational potential energy. And your work is going to equal to delta KE. And we said that the work is minus delta PE. So that means your total network is your kinetic plus your potential. Now, your total work is all your conservative plus all your non-conservative work. Where your total work is your change in kinetic energy, which is your kinetic energy final minus your kinetic energy initial. We said that the conservative, that's your potential, is going to be mgh initial minus mgh final. Having to do both of them, that means your non-conservative work is going to equal to delta Ke, which is this one, and this is going to be minus delta Pe. Plus delta Pe. Let me go ahead. So actually, let me write it down like I had it earlier. Delta. Oops, page. Yeah. I'm going to write this down on this page so that'd be like just clear. So non-conservative work is delta Ke plus delta Pe, which is in this case, it'd be kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And if you open them up, what you're going to get kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial, which this is going to equal to, let's do the finals together. Kinetic energy final plus potential energy final minus, sorry, kinetic energy final. Yeah, potential. Kinetic energy initial plus potential energy initial. This is going to be your energy final, and this is going to be your energy initial. So your non-conservative work is going to equal your energy final minus your initial energy. If your non-conservative work goes to zero, that means your final energy is going to equal to your initial energy. So let me go ahead and write this down. If the network on an object by a non-conservative work non-conservative force is zero, that means the energy don't change. Which means your if non-conservative work is going to equal zero, your EF is going to equal to EI. Let me go ahead over here. So your final energy is going to equal your initial energy. So your MV final square over 2 plus your MGH final is going to equal to MVI square over 2 plus your MGHI. your masses cancel out. And what you're going to have left? You're going to have your final square over 2 plus your GHF is going to equal your initial square over 2 plus GHI, which means solving for your final velocity is going to equal to 2 times G times HI minus HF plus your initial velocity squared. Now, one thing I want to mention that let's say potential energy, I'm going to call it U for a second, just to follow the book. That means your change in U is going to equal to your mass times gravity times your H final minus your H initial. Now, we're dealing with the y-axis. So I'm going to say it's mg y final minus y initial, which is going to be your mg delta y. And this is going to be your gravitational. So basically, your potential energy gravitational is going to equal to mg delta y. So let's do a little example. You got a gymnast that leaves on trampoline at initial height of 1.2 and reaches a maximum height of 4.8 before falling back down. What's the initial speed? Okay, let me go ahead and do this one. This example real fast. Example 7, that's example 7. So we have a H initial of 1.2 meters. Your H final is 4.8 meters. And you're trying to find the final velocity. Or sorry, the initial velocity. And you know your work is your change in kinetic energy, which is going to be your 1/2 mv final square minus 1/2 m mv initial square, which is going to equal to the change in potential energy, which is going to be your m minus change in potential energy, which is going to equal to your mg hi minus hf. So basically, your mg, and I'm just going to write this down, hi minus hf, this is going to equal to minus 1/2 mvi squared. This is going to go to 0 because your final velocity is 0, which means that the initial velocity is going to equal to minus 2 times g times your change in hi minus hf. And in this case, it should equal to 8.4 meters per second. Go ahead and check. Yep, we are correct. So Definition of a conservative force. A force conservative when the work it does on a moving object is independent of the path between the object's initial and the final position. The force is conservative when it does no work on an object moving around the closed path, starting and finishing at the same spot. Which we talked about this, the force conservative when it works done on a moving object independent of the path between the object and final position. We did the basketball example, which we did the gravitational potential, the gravitational potential energy, which is going to be your mgh. Now, examples on conservative forces: your gravitation, your elastic, and your electrical forces. Non-conservative includes your resistance, your tension, your normal forces, or static and kinetic friction forces. We also define the work as FD cosine theta, which is going to be for non-conservative force is the kinetic frictional force. In this case, it'd be minus F times the distance S in this one times cosine 180. Cosine 180 going in the opposite direction, so it'd be negative. So we define what the full work is your conservative work plus your non-conservative work, which is going to be your change in kinetic energy is going to equal your potential energy, your minus potential plus your non-conservative work, which we got to do the work energy theorem, which is going to be your delta KE plus your delta PE. And that should conclude chapter 7 for our class. If you have any question, please email me abunaemeh@gmail.com. Have a nice day.